Okay, that's that. Let's put a lid on linear response and ask ourselves, what about nonlinear response? What if matter's response is not linear? What do we mean by this? By this we mean this one simple fact, one simple feature, and that is, so far P, what's P? P is the polarization field. Okay, it's a function of R and T, but let's keep everything simple. Was epsilon naught times chi times E, the electric field. Is this always true? Well, as good physicists and engineers, we must ask the question, what if this isn't true? What if we admitted a Taylor expansion? What if we admitted this? All right, we can. But what would be the consequences of this? Let's examine this. So, what if matter's response is not linear? This question should rock us a bit, shouldn't it? We are rocking the boat. So, let us rock it and see what happens. So far we know that molecules are excited by laser light. We say laser because we need, as we will realize, that we actually need substantially a strong source of radiation or light to induce or push us to consider nonlinear response. So light causes here molecules, a representative term for atoms, a unit of lattice in a condensed matter medium. All of these are what we mean by an atom. We say that the light beam polarizes a medium. Okay. So this is polarization in nature. This is not the linear polarization of light. By this we mean to say that either the medium the molecules need not necessarily have a non-zero permanent dipole moment. So a molecule like CO2, a symmetric molecule, OCO, carbon dioxide, does not carry a net dipole moment. Okay. O and C have different electron affinities, if I may use such a term from molecular physics or chemistry, but then the differences in this sort of cancel out. So you can look this up in terms of the dipole moment of CO2, whereas water may have a permanent dipole moment. H2 or H2O or HOH can carry a permanent dipole moment. In both scenarios, a laser beam incident on a medium, that is in a cell containing carbon dioxide at room temperature, that is 300 Kelvin, or a cell containing water which is in its liquid phase at 300 Kelvin and ambient pressure, that is 1 atmosphere or 1 bar. If I shine a red helium neon laser, for example, right, what happens is, as the laser beam propagates to the medium, in terms of CO2 for that matter, light polarizes the medium and it responds. Okay. In the case of a molecular entity without net dipole moment, this will induce a dipole moment by separating the charge centers, the positive and negative charge centers. In the case of molecules which may carry a permanent dipole moment, what the electromagnetic wave can do is that even though individual molecules can have no net dipole moment, they are often randomly oriented in a medium. There is no reason to presume a specific orientation. So, each of these individual P's can point in different directions, so that the sum of individual Pi's vectorial sum is 0. Yeah, without the application of a field, that is no laser light, this is the light, this is the scenario, whereas yes, for the laser light we could have a fair degree of alignment. Not that we have perfect order and everything comes to nearly zero entropy for this system. No, not necessarily. Earlier all we had was, if I take any direction, say vertical, there are the sum of Pi had as much positive upward amplitude, it had as much along this direction as it did along this effectively, and these two cancelled out each other and we had 0 total polarization vector. But now with the light field incident, it can induce a net polarization and net dipole moment along the direction of the oscillation of the electromagnetic wave. Of course, here we are considering linear polarization of the electromagnetic wave, right. So, these oscillating dipoles further emit light, further emit electromagnetic waves, okay, in unison, collectively and coherently. Look, they are all oscillating in phase, they are like one giant or one very ordered society, okay, where each one emits in phase with respect to the other. Okay. Now, the question is the following. Earlier, recall, for this motion we used xc for the displacement between the positive charge center and the negatively charged electron cloud. We had a net displacement of these two charge centers and we called it xc. Whatever may have been the details, okay, whatever may have been the details, this response oscillated at a frequency exponent I omega t when the driving field was, say, E naught cosine omega t. The response of the medium was at the same frequency as that of the incident light wave. This is why we are used to the notion that frequency does not change, although wavelength can adapt itself by a factor of n, the real part of the refractive index. This is the hallmark of linear response. Xc was always oscillating at omega t. What did this mean? If I plotted x as a function of time, what is the 0 of xc? 0 is where the atomic nucleus is. Excursion in the positive or negative direction is just two different directions of excursion for the electron cloud in this 1D model, right. So, what we said earlier is that the response is taking place at omega. So, this is exactly what is happening in this oscillating cartoon that I am showing. They are getting displaced away from the atomic center owing to the fact that this is the direction of polarization for the electromagnetic wave, right. So, this is important. Now, driver at omega Xc is also only at omega, the same frequency. The question we are asking is, what if this motion is not sinusoidal for any reason? Linear response implies sinusoidal motion of this atomic cloud, right? What if this is not sinusoidal? What happens? We have experienced this in everyday scenarios. So next time you go to a concert, whatever, next Sarang festival, watch out, especially when people are trying to tune their audio system, or in a hall with relatively, poor layout for the acoustic system. You have a speaker and person holding the mic goes too close to the speaker, and what happens? You hear a very high frequency shriek from the system, which instantly causes at least some amount of discomfort to a listener. So why is that happening? Okay. So if you play music through a cheap amplifier, which could well be the case, okay, such as an old age FM radio as compared to our cell phones, which seem to have pretty good amplifiers, but probably that's one scenario. Or why you would spend an exorbitant amount of money to buy a very high quality pair of headphones, right? That's because that has a great amplifier where these distortions do not take place, or they are minimal. The input wave is sinusoidal and the amplifier is true, okay, it is a faithful amplifier, or it is high fidelity amplifier. That is why it is hi-fi, comes from the original term high fidelity. If the amplifier is high fidelity, it faithfully reproduces every frequency proportionately in amplitude, but with amplitude amplified by a factor of 3 times or 5 times or 10 times or whatever the case may be, whereas in a not so good amplifier, its response gets truncated beyond a certain point. But this is the time domain picture of things. A simple example from acoustic amplification and audio, where we have a non-sinusoidal response to a single input frequency when some processing of the signal takes place. If we Fourier transform this thing with sharp edges have high frequencies, or elementary considerations right away say that whereas we have a sinusoidal wave of this type in time, if I have a set of trapezoidal pulses, or a trapezoidal wave, then we have learnt even in our own considerations in Fourier transformation, that this is a sum of one constituent sinusoid at the same frequency plus maybe at a smaller amplitude a second harmonic for the sinusoid, a third harmonic, and so on, of the original fundamental frequency omega of the wave. So we have a wave at omega, we are forced to consider waves at 2 omega, 3 omega, and so on. I have done nothing in optics in bringing all this up to discussion. All we are saying is, look, you can have these things too. Okay. So that can also be done with light. Start with red light, and if the response of the medium is not linear, okay, start with red. Let us go to the far end of the spectrum, maybe infrared. Let us say we start with 1634 nanometers, which is a wavelength at which a popular laser emits radiation, and this radiation goes through some medium and this medium can have a response when it is linear. You get back 1064 nanometers. However, if the response is not linear, you get a half of this wavelength or twice this frequency out. That is nonlinearity. Simple. The medium has had something else other than linear. Even if I do not know what, the immediate guess is that whatever be the distortion, the next term after the leading term in the Taylor expansion in the response of the medium is a second order term. If that is for any reason 0, which it can be, then the nonlinear response can be 1/3 of this, okay? That is approximately 366 nanometers, a third. So, lambda, this is lambda omega, so lambda over 2 and twice omega, this is lambda over 3 thrice omega. So, the most immediate consequence of a not linear response, non-linear response is a response at other frequencies. You send in red light, but you get a red and green patch both. You get some frequency conversion. This is again why earlier we did not consider any frequency conversion in linear optics. We were always told that by in earlier education that look, frequency does not change, but wavelength will. If frequency had to change, its only opportunity in this picture, if I may say so, is for it to become twice, for it to become thrice. A gradual variation isn't an option like wavelength. Well, you can argue that there are scenarios where there is fluorescence, which is an inelastic process. That's owing to an entirely different scenario. These effects are still, no matter what, these effects are not absorptive. This effect is refractive. These only concern the real part of the whole series of guys. You do not need to consider absorption. That is to say, it is not as if 2 photons of omega 2x of h bar omega is actually absorbed and 2 omega fluoresces out. It is possible that one can think of it. It is a clever argument if you wish, but that is not really the case. That is a different process. 2 photon absorption is different from second harmonic generation. Okay, I must just I'm just trying to clarify this. This is absorptive. This is refractive. It is not absorptive. No. The harmonic generation process is a refractive, non-absorptive process. It is non-resonant. Please keep that in mind like forever. There will be pictures of these processes where you are told that it is some virtual states would be involved in the absorption and so on and so forth. That is a different story. This is simple This is simply arising out of essential superlinear or nonlinear response of the medium. A spring can undergo this. Okay. So, essentially nonlinear response is a fundamental response to the atom. Okay. If this is the potential well in which the potential of created for the electron, the Coulomb potential, okay, as a physicist would write it, which scales as 1 over r, the potential energy between two charges is a constant times value of charge 1 multiplied by the value of charge 2 divided by the separation between them, right, which is a k, we were told this is q1, q2 by r, the separation, right. So, r could be a vector even. So, that is what, so therefore, the potential is in terms of an electron, the harmonic motion that we spoke about for this electron essentially occurs by getting displaced about the nucleus. You see, the electron's oscillation would still have to be within the perimeter that is marked by the potential of the nucleus. That is why the electron is bound as yet. So, I can now model the response of the potential that is considered here, the 1 over r potential or any potential that binds an electron to one or maybe electron cloud to one or even more than one charge centers, as in the case of molecules, right. Whatever be the detail, what we can picture is a coordinate axis, a physical coordinate axis, which is r, which denotes the displacement of the electron from its equilibrium position. The electron cloud is displaced from its equilibrium position to some extent. Okay. If an external field is applied to it, it can be pulled away from it, but it encounters a reflective wall, a reflective potential wall, and it goes back to the mean position. The mean is actually over here at the minimum of this well. So, an electron cloud can simply perform oscillations inside this well, in this case the entire well. This is all legal space, whereas on the other side here, this red hashed region is forbidden. The electron can simply not do excursions out of this. Okay. Classical physics forbids the electron with this energy to escape this potential well. Okay. The only way it can escape this potential well is to raise its energy, go up the energy ladder, raise its energy, go up, and that is the way out, if at all you want to pull the electron out of the system. But the point that we want to make is that for small displacements about the mean position of the electron, for small displacements, no matter what the shape of the potential well is, for small displacements, we can approximate it by the potential of a harmonic oscillator. If the excursion is much larger, then the electron goes into not harmonic or anharmonic territory. It can, between the red curve and the yellow curve, there are, and the red curve and the blue curve, within the allowed region for the electron to make excursions, the electron cloud to make excursions, there is still space which is not covered by the harmonic approximation. Harmonic approximation is what led us to linear optics and linear response. Okay. But a systematic way of thinking about this potential in terms of going beyond the harmonic approximation is to add higher order terms, always tailor it out. Harmonic term, then we can have a positive quartic term, a negative quartic term, do all these modifications to the distortion coordinate x of the electron cloud. Okay. So, the moment we go away beyond the harmonic approximation, just as in the case of a Hookean system in very elementary considerations in physics and mechanics, mechanical analog. Hooke's law, the Hookean response is f is equal to kx or minus kx. K is restoring, so it always pushes you back towards the 0, right. So, linear region is marked by kx. Earlier, if you recall studying this anywhere, we would have said, oh, okay, this is up to Hooke's law, these are all, the region here is beyond Hooke's law and can have a whole set of mechanical scenarios occurring over there. So, look at the dashed versus the dark line. For large displacements, the response of the system is not linear, a whole lot of effects can take place there as well. You can have generation of harmonics, you can even have some hysteresis, which is memory in the system of the thing having pulled up. Even in optics, we can have such nonlinear responses can involve memory. Where do we see this? In good old optical storage media. It is nonlinear response and it has hysteresis is what storing the information. You can convert the optical wave into charge. Okay. In photorefractive materials, the electric field, the photons absorbed turn into charge and they are stored as volumetric storages. They can have really very dense data storage, they can bring very dense data storage opportunities to the level of petabytes, which is really huge, which magnetic media, for example, cannot always match, but then other factors come into consideration. Read and write and read out issues, then costs more important than anything else and so on. But then we did have an era where optical memory in the form of compact discs, DVDs and others ruled the market, and those exploited optical response, but of the absorptive, those exploited nonlinear optical response, but of the absorptive type. Okay, you need to put something in and store it there. Okay, so in normal optics, when a light wave acts on a molecule, the electron cloud vibrates and it emits, which emits its own wave, which interferes with the original wave. This is the typical model we have. So, we can also imagine a process in which the molecular energy levels get involved, where light is absorbed. You promote a system from a lower to an upper state and absorption can take place. These are all linear optics scenarios, whereas excursions to the nonlinear regions distort this perfect harmonic motion. This is the electric field and earlier the dipole followed this, whereas nonlinear response essentially means the x of E t, or the in terms of Maxwell's electromagnetics, the polarization vector P has a response which is not anymore harmonic. You see, your response is beyond linear and you have essentially the excursion on one of the sides, okay, having a lesser maximum. This is a distortion of the sinusoidal response. If we have this response over here, total response, needs a Fourier decomposition into the fundamental polarization with a frequency as that of the incident wave, frequency omega, plus the next term in the Taylor response, omega, twice omega. But remember, this response also has a DC shift written into it. If you watch it carefully and not get misled by the zero line, the whole wave has shifted in DC sort of by some units upward. So, a steady DC polarization also is required, right. So, two important messages: color will switch for the incident, a part of the incident wave goes from red to blue, 800 nanometers near infrared, 400 nanometers in wavelength, blue color, violet blue region. That's what the second harmonic response would entail. But there is also a DC shift, okay, in the polarization. We did not consider DC terms earlier, but nonlinear optics is pushing us to do that, if you wish. So, this is a very interesting term. It's a rectification in terms of electronics language. If you have a AC to DC converter, you called it a rectifier. See, so this is rectification, an optical rectifier is at work. Can you use it? Can you measure it? It's very good questions. We will see.